It's a great honor to be here. Thanks for having me here. And I'm looking at research, so I take a little bit of a step back on the technology exploration in this deterministic communication. And maybe I start with, what is deterministic communication? And this is something that, there's a couple of activities that have been ongoing, and there has been an article which nicely described this. It says deterministic networks is about having reliable and predictable network services which have bounded latency and also low delay variations, and you can apply and no packet losses, and you can apply them to deterministic flows. And that means it is something where you can differentiate traffic. You can provide the right service for a service that requires this kind of behavior. And that may come at the cost of that you prioritize it over other traffic which is more flexible of accepting variations. So it's a part of quality of service management procedure as well that you have in these networks. And you want these networks to be able to be scalable. So some use cases are very localized, but there are also other use cases which are more in larger networks. And some examples of the standards that are ongoing in this is time-sensitive networking, which is basically an addition to the normal Ethernet global standard that provides this time-sensitive and deterministic capabilities. There's also work in IETF on deterministic networking, which is kind of a similar approach, which is brought to IP-based network infrastructure. And then from the wireless side, we have, of course, 5G, which introduced reliable and low latency communication. Now, one example that is often given, and we had the presentation of 5G ACA earlier today. Often we come to this smart factory where we see that there's a wide range of use cases that you find in such a factory, and several of those are in this. Have these requirements that they require deterministic communication, so like that you have real-time representations of the production processes or real-time monitoring of the processes, but also optimizing the productions by controlling how processes are being handled. And it's not surprising that we often come back to this factory, because I would say the beginning of deterministic communication comes from the industrial segment. It was already in the 80s that a lot of specific technologies were developed in order to achieve deterministic communications, these entire range of field bus technologies. And on the right-hand side, you see a little bit of the market situation. So there's a large number of different field bus technologies. Later, industrial real-time, industrial Ethernet variants were being added, and they are all basically specific technologies to address deterministic communications. In total, it's a rather fragmented market, which is non-compatible. Some of these standards are linked to certain applications, and they are applied in smaller network segments. So it's quite complex from the system integration perspective to operate a large-scale network where you have these different technologies integrated, which means they are per se insufficient as a general platform for deterministic networks. And the big driver and we have heard that earlier today as well, for this is the Industry 4.0 transformation, where we come from the left-hand side, from this hierarchical structure on how factories are built today. But even these industries, they want to utilize all these enablers of digitalizations. They want to get access to machine learning, AI, cloud computing, and that means that doesn't work well with the structure on how these systems have been built in the past. They want to get access to a digitalization platform and connect all their assets in a fully connected way. And how this is done traditionally is that you have your system, which is basically compartmentalized and segmented into these different areas in which you have then full control of what is ongoing, and that gives you the deterministic on that level. But it means if you want to make these transitions to this, getting to this local compute infrastructure in a factory and applying your machine learning for predictive maintenance and whatever, then this is basically a burden. And that is why this strong push has been for enabling this transformation from a network side by enabling a fully connected design throughout this entire system, which means scalable from the small scale to the entire plant level. And this is where we have basically this where the story of TSN comes in, where we say Ethernet is already the common platform for communications in the non-deterministic side. Can we add the capabilities for real-time communication into this platform? And that is how the TSN standardization has started some 10 years ago, and where a lot of these capabilities have been added as add-ons to the standard Ethernet standard. And what you can see is that this quite diverse industry is converging in their view that this is the way to go, because they come from a history where they have this diversity, which is non-interoperable, very segmented market, fragmented, and with the TSN, they basically have an alignment of the industry and basically putting their common forces onto one technology basis. And that's why we see so much of this focus on TSN. And then IETF.net is something which is taking a similar approach. They're working very closely with TSN standardization groups as well for bringing similar concepts into larger IP network domains. It's not for the general internet. Everything that we talk about here when we talk about deterministic communication means you need someone who is in control of managing these networks, which means all of this applies in single administrative domains or few administrative domains that are coordinated. So that is nothing that scales up to the full internet, for example. But even if there are these trends that I have shown now for bringing deterministic communications in the wired communication standards, there are some shortcomings. And that is that or to put it differently, there's a high value for going to wireless. And this is simply because, we have, for example, if we take Industry 4.0, we have a lot of flexible and dynamic production changes. That is the big trend of the industry right now. And there, with any connected or wired connectivity, you are simply in limitations. You cannot easily adapt to this flexibility. Then we have a lot of use cases which are based on mobility. We have mobile robots, automated guided vehicles. We have human-machine interfaces. In future, maybe AI-enabled glasses or tablets that you work with, or adding sensors to the assets that are moving around in the production. And that means these are use cases that cannot be addressed at all in a cabled manner. And that means, in general, by bringing this kind of concepts into the wireless domain provides a high value to these industries. But then, we come now very much from the manufacturing side. If we look a little bit more into the future, we see that we have a general trend where we will have in more and more areas physical assets, physical machines, a physical environment that is connected to a digital representation, often digital twins. And out of this digital side, you observe, you monitor what is ongoing in the physical reality, and you can control what is happening there. And we see that this area is spanning, so it comes very strong from the cyber-physical production systems, but this is something that will affect very many fields of society, of enterprises. So this is a general theme that we see increasing significantly. And which means in the 2030 timeframe, we see that we move towards a more and more cyber-physical world. And 2030 is then, of course, in this industry something where we look into from a 6G standard perspective. So from 6G, we want to make sure that we have a platform in place that enables this transition. And that is something which is a broader trend that goes beyond manufacturing, where maybe a lot of this started, but we need these kind of more dependable and deterministic communication. But then it's not so that we will we wait now for 6G. That's a story that is starting right now. So we are already with 5G on this track towards this direction. And that is why this needs to be ongoing continuously. And as we heard earlier by Xeli, if we go to the manufacturing industry, they have life cycles which are much longer than our generations in mobile communications, which anyway we need some kind of consistent story. We evolve and provide new capabilities to address this. So to start from, what we did in 5G, then in this TSN direction is that we provided the solutions for building non-public networks that you can put into these manufacturing plants, for example. And we work in the standard for enabling this interworking or integrations with the time-sensitive networks. And that is done by providing interworking functions in the control plane and in the user plane, and thereby integrating into this larger TSN network, enabling time synchronization and data traffic for that. And in Release 18, some similar work is being done towards support of that node, which then also enables IP-based deterministic networks. I think we have seen a similar slide before. There have been different steps in the standardization, from setting the foundations for low latency and reliable communications, addressing more the industrial IoT needs in the standards, something for scaling up the capabilities of these networks, and now in the latest release more expanding in the use case dimension, addressing, for example, extended reality, but also adding DetNet support. But when we come back to what is the foundation of deterministic communications, then I think it is about being able to transmit the right packet at the right time. And that means we must be able to have a bounded latency, but also provide a bound on the packet delay variation, or jitter as sometimes called. And why is this needed? And one of the reasons to do this is that you want the communications to be plannable for the external domain. And the external domain can be either the applications themselves, which want to plan for this is exactly when my packets arrive, or it can be in case of something like TSN, where we have a larger network infrastructure which has a control plane that tries to manage this network. Then you need to make the communication plannable from the TSN controller. So this plannability is one important feature in this deterministic communication. And when we look into trial activities with 5G in different POPs, then we see that actually there is a rather large packet delay variations that we find in these systems. And of course we have, and reasons for that are multiple, which are part of our wireless systems. There's the TDD pattern, which of course has a certain periodicity, and the latency depends on when your packet arrives with regard to this pattern. We have hybrid ARQ, which is an extremely spectrally efficient way for providing reliability, but it comes at the cost of providing variation. And we have shown that for some use cases for a TSN controller, it can be quite difficult to handle this because you're not so plannable if you have variation. And of course, we have standardized ultra-reliable low latency communications to push down the upper bound. But even in systems which have a low upper bound, we see that we still have a rather large packet delay variation. So there are ways to get rid of packet delay variations. For example, one approach can be that we simply say, well, we compress this variation to a smaller value, something which we talk about as packet delay correction. And something like this was actually discussed in the Release 16 standardization SA2, where when TSN was being introduced, and it was called then de-jittering via hold and forward buffering. But then this standard was, Release 16 was coming to an end, there was time pressure, there was not enough time to finalize this, so this hasn't been done there. But this is something that, for example, removes this variation. What we are also exploring from the research side is, of course, this plannability from, if you go, for example, for TSN, is that at the moment a TSN controller simply accepts that you have a very tight bound of the variation. And of course, you can also make it smarter in a way that it can accept variations. And that is something which can also provide benefits of having this. But otherwise, what is to be deterministic, you want to be able to somehow say, what is my upper bound, for example, by using capabilities of ultra-reliable low latency communications, and then have a mechanism of saying, and can I also remove the variation? And we have been looking into this now in several collaborations. And I actually think that we also should think by ourselves, what is the questions that we are after? Is it really determinism which is so important for us? And I'm actually propagating that we should move away from deterministic communications, more think about dependable communication. And the reason is this: when we talk with our partners in the industry, they often, if someone who comes from system engineering, they often have a very strict definition of determinism, and that is simply, if you have stochastic variations, you're not deterministic. Or another way to saying, well, if we have a system which is in a given state with a given input, you must be exactly possible to predetermine what the output state will be. But then there are simply fundamental stochastic variations in several components of the digitalization enablers. Wireless communications for sure has stochastic components. But the same thing if you have an industrial industry which wants to cloudify their controllers. They also go from a deterministic compute infrastructure to a stochastic compute infrastructure where they get invariations. And they are building more adaptive applications, which means we see that in general the available or the presence of stochastic elements is increasing. And that could you could take this to say, well, maybe there's another approach to this, and that is when instead of eliminating all stochastic elements, which is not always feasible, maybe we can embrace them and handle them in a good way, making even stochastic elements predictable and plannable. And what we are really after is that we can manage the requirements and support the applications. And that means, so if we go again to systems engineering, they use the term dependability, which means the applications can rely on that. If the network performs as it's said, the application will work. And that means so I think deterministic communications from its definition is something which describes very much how the system, what the internals of the system, how they are. Whereas dependable communication describes more what value can you create towards the application. And with that we are looking into these dependable mobile networks for time-period communications, and one way to describe is that you want to be able to ascertain that you can deliver a certain service performance according to what you have agreed with the application domain. And there are several components that are needed in this step. The first one is, first of all, we still have time-critical services, which means some toolbox for low latency. And so the first bullet here is something that you need. But the second thing that you also need, you need observability. You must be able to quantify how well do I actually work as a network. What is it? What are my characteristics? And if we can understand this and describe it, then we can go into the interactions with the application domain on having a rich service specification, on what is it that the application really needs. And then, of course, you must be able to deliver, to monitor what did I deliver, did I fulfill my service level agreement, and that you can come into an interaction with the applications. And there are actually ways on also how applications can be network aware and can be more robust if they are aware of the characteristics of the network. And that is something that we investigate now explicitly in a research project which is called Deterministic 6G, where we work together with industrial partners as well in identifying what is the right way of making sure that we from the network can deliver on what you really need. And with this, I'm at the end of my presentations. There are a couple of references if someone wants to follow up on a bit of work. Otherwise, I'm open to any questions.
Okay.
Thanks.
Thank you very much. Joachim.